So welcome back, everyone. We'll continue our dive into deep neural networks. We have seen in the previous submodule why it's good to have deep neural networks. And now in the second submodule of this chapter, we'll be analyzing the problems that can occur when having deep neural networks, and what will be the mechanisms to address these. So we'll study the problems with depth. Okay. So although we have seen previously that deeper is better, practically that was the main takeaway messages. The message for decades, well, in a long time, the training deep neural networks was highly challenging and unstable. So and this was not just limited to the well, limited hardware that we had and small amounts of data that we had at that time, but there were also some algorithmic flaws that have been addressed and fixed in the past 10 years, practically, in the deep learning revival. And we'll study a first one now. And you might have heard of this, but one of the most known challenges at that time in the early 2000s was the so-called vanishing gradient. So what does this mean? So actually, when we were training deep neural networks with many layers, we could see that small gradients, there were small gradients, and the side effect of those was that they were slowing down and eventually blocked the SGD, stochastic gradient descent, and also had the limited, they offered a limited capacity of learning because people were afraid of these vanishing gradients, were trying to avoid them, so practically they were stuck with small neural networks just to avoid them. So we will see now why did we have this vanishing gradient problem, and what simple solution researchers have found to address it. So here I take a snapshot from a paper by Glorot and Bengio in 2010, and what they were doing, they were taking a 5-layer neural network and looking at the gradients, and they were plotting the occurrences for different values of the gradients. So we can see this layer 5 cyan has quite a broad spectrum of values. So we have quite a few points outside of 0 in both positive and negative. The before last layer, the 4th layer, so we start the backprop from layer 5 to layer 1, right? So from the loss, we start backpropagating the gradient as we have seen in the previous courses. So the gradients in layer 4 are based practically also on the gradient information that is coming from layer 5. So we can see that they are still looking quite nicely. They're relatively distributed across the spectrum of value, the range of values, although you can see that they start to there's a mild effect of gathering them around 0. When we go one layer further, so practically towards the beginning of the network, we have layer 3. We noticed a similar trend, right? Since they're based on the gradients from layer 4, we can see that they start to be also starting to go towards 0. And doing like that, we can see that the layer 1, the first layer in red, we can see that it has most of 0 gradients. Right, so most of the gradients that it receives are either 0, either very small. Right, so this doesn't allow it to learn much. And actually, because of this, at some point, what people were doing, they were doing what we call layer-wise pre-training. So practically, you were training a network just with a few layers, or one layer. You were training just this layer. You were taking the head off, adding a new layer, and again putting the loss there, training just the second layer while keeping the first layer frozen, then adding a third layer and fourth one, and so forth. Well, you could add also 3 layers at a time, and it doesn't matter exactly the implementation details, but you had this layer level pre-training where you had to train into different stages just to avoid this problem of having the gradient vanishing and not learning at all. So where does this problem come from? I mean, is it just a problem of depth? Because, well, now we have deep neural networks. What did change? So let's analyze a bit deeper what's happening in a 3-layer MLP. So we just write it down on a per layer basis. So we have our neural network. It's f of a given input and three W's corresponding to the parameters of each layer. and we have some sigmas, which are the intermediate, which are the activation functions, right? So we have at the first layer W1 multiplied by X. We pass them from sigma, then we multiply the output by W2. We have another sigma, another activation function. Multiply the output by W3 and sigma. I note that I'm omitting here, just for clarity, I'm omitting the bias. So you have also bias term that is missing from the equation. So if we write it down in a more detailed, unrolled manner, we can see that if I, well, in the first layer, I have U1, which is W1 or X. U2 is a sigmoid. Let's say that we have a sigmoid activation function of U1 and so forth. So we have this chain of operations in the forward pass. When we do the backward, we want to compute the derivative with respect to of the output y hat with respect of W1, which is the layer which is the weight in the first layer. By using the chain rule, we have to pass through all these intermediate values, right? So we have dy hat by dy u5 multiplied by the partial derivative of u5 divided by the partial derivative of u4 and so forth. So well, with respect to u4 and so forth until we get to our du1 by dw1. If we group them also by the activation functions, we have here, we can see here the sigma u5 by u5, w3, du3 by u3, w2, du1 by u1, and x. So we just compress them by adding the sigmoid here. And the sigmoid was very popular at that time because it's a really nice function. It just squashes your values between 0 and 1. It's stable. It has a nice derivative, which is here. So it's really easy to compute, but it has a big flaw. So as you can see, when we plot the values for the derivative of the sigmoid, it has this range of values, and the annoying thing is here. So as you can see here, the maximum of the derivative of the sigmoid is at most 0.25. So this is the best case scenario, right? When we're exactly in the middle. So if you remember the sigmoid, here it goes like that. So here it's exactly in the middle of the point where you have the highest steep in the sigmoid. So afterwards, it comes to vanish. It vanishes. It goes lower and lower. And here, whenever it's 1, there is practically no slope, and the value of the sigmoid is 1. There's practically no slope, so the derivative is 0. And the same when the sigmoid is 0 and it converges in the infinite to 0, there's practically no slope, and the derivative, it will be also to 0. Right. So if we put back this into the chain of multiplications that we had before, so we see that we have something which is less than 0.25 multiplied by something which is less than 0.1, assuming that our weights are initialized randomly from a Gaussian of 0 mean and small variance. And usually the weights will be like that. So this is quite classic. We'll multiply with something which is smaller than 0.1. Again, something which is smaller than 0.25. Something's multiplied by something which is smaller than 0.1, and then something which is smaller than 0.25. So we can see that actually the gradient that is supposed to arrive at the first layer practically exponentially shrinks to 0 as the number of layers in the network increase. So this is what we call this is the reason, the cause of the vanishing gradient problem. So for this type of problem, the sigmoid and the tan H, and in general, the bounded activation functions are prone to this. And also there's the initialization plays a key role here. So here I was actually nice initializing with the 0 mean and small variance, but if we have a bigger variance, it might go into different different sides, and well, it might actually impact the sigmoid, which will be somewhere towards 1 and 0. As I said, it's quite important where we are in the sigmoid, because at the peak we have 0.25, but imagine that our weights will be somewhere in here. So if they would not have been centered around 0, then the problem would have been even more pathological. So even worse, because the derivative here would have been even smaller than that. So at that time, it was actually quite common to try several initializations, several random seeds, and have several experiments going into nothing, and then having to resume. So which was also a reason for why people, in particular in computer vision, were skeptical about deep learning and, well, neural networks in general, is that you had this dependence on random seeds and this instability. And it was believed that, well, practitioners in the neural networks were having their own dark magic and specific toolkit to use to make sure that their networks are training. So how this was solved, I guess Mark gave you already a part of the information in the first course, is with the arrival of the ReLU. So the rectified linear units, which is a very, very simple activation function, is practically the maximum between 0 and the input. Right, so whatever is lower than 0, it's 0, and whatever it's higher, you have just the identity. And behind this very, very simple simple function, there's a very, very nice property which is visible in the derivative. So if you compute the derivative of the ReLU, if you show it the first order derivative of the ReLU, you can see that wherever it's positive, the output is positive, the derivative is 1. So this is really simple. And then for the other cases, and the 0 is 0 because there's nothing to pass and nothing has changed there. So in general, when for x equals 0, normally by the way the function is defined, this derivative is undefined, but most neural network frameworks, usually set it to 0. So when we come back to our previous setting, when we replace the sigmoid with the ReLU here, the sigma, we can see that now we have something which is 1, 1. So it has a much cleaner and implementation. So it avoids this vanishing gradient problem. Again, provided that we have a good initialization and the weights and the biases lead us to activations which allow us to actually compute non-zero gradients. So what we should note here is that the ReLU unit dies when its input is negative, so it puts 0, and this blocks gradient descent. But on the other hand, induces sparsity in the network, which is actually a good property. If we have a problem with this sparsity, what we can use is the so-called leaky ReLU, which has a small parameter alpha that is used to multiply the input x whenever it's a negative. So basically, instead of having a 0, we just have a small, mildly decreasing slope. And when we see this in practice, just to show it, because it doesn't just not help vanishing gradient, but it's also in addition to that, it speeds up training. So we can see here in dashed lines we have the training loss for a network with sigmoid activations. Sorry, TAN-H activations. While in black, in solid, we have a network with ReLU. We can see that we get to the same points after 6 epochs. Compared to 36 epochs that we had for the previous. So it's a huge boost and a huge contribution in the deep learning research. So there's other ReLU-like alternatives that have been proposed in the recent years. So this is the leaky ReLU that I showed you before. There's a smooth ReLU which goes a bit like that. It never goes to 0. So it has this beyond in the proximity of 0, it looks a bit like this sigmoid, but then upwards it goes like a regular ReLU, and various variants of ReLU, leaky ReLU, parametric ReLU. Actually, I can just visualize some of them, and I really like this visualization because it allows us to. They also show the first order derivative. So, for example, we can see the sigmoid. The sigmoid in blue we have the original function, and in orange the derivative. So we can see the huge limitation that it has to with respect to the values of the first order derivative. And at some point, people were saying TAN-H is a lot better. And indeed, it was better. So tan h is similar to sigmoid, but it squashes between -1 and 1 instead of 0 and 1. And since it has a bigger steep here in the curve, it allows to have a bigger derivative, and we can see the derivative of tan h goes to reaches 1. But again, whenever we get to these regimes, which can be prone also to bad initialization, the gradient will be again 0. And let us compare with Liquid-ReLU. So Liquid-ReLU, we have here a small parameter alpha that allows us to not be always 0. It just goes like that for the negative. It's close to 0, but not quite 0, so we can still recover some information from there. And then, well, I'll let you have fun and analyze various other functions. So this is the parametric ReLU, where we can either learn well, we can learn a certain parameter to give to the network so the network practically alpha is a weight of the network, and it's trained by gradient descent. So it learns the parameters of the ReLU such that it will find the best trade-off in terms of sparsity and performance, right? So it will decide how much by how much actually to reduce the gradient in this region. So if I put something like that, we can see that with 0.2 it has a mildly decreasing slope, with 0.1 even milder, and hence also the gradient is smaller here because of the slope. Okay, so coming back to our activation functions. So, well, this is still subject of study in well, finding the best activation function is still an open area of research. Well, feel free to explore whatever you feel like, but yeah, always pay attention to the gradients and how they look like before you apply them. It allows you to better understand the intricacies of these activation functions. But if you want just to have something vanilla, ReLU is a very safe choice. So if you don't want to overthink too much on what to do, to over design too much in your architecture, you are safe with ReLU. So this one of the problems, as I said, was with deep neural networks was this vanishing gradient problem, and another one because we have these big neural networks is it's related to the regularization. So more specifically to the overfitting of these neural networks. So you might remember from the previous module that we were analyzing this curve. The blue is the training loss, and the red is the test loss on the evolution of the performance with respect to the capacity of the network. So at that time, I was saying, well, we know that in traditional machine learning, the bigger the capacity, the higher the risk of overfitting, because we have this huge gap between this big gap between the test error and the train error. To some extent, we can control. We have seen that having a big capacity actually can mitigate some of this, because we had this double descent curve. But in order to reach there, we have to be very careful, because the neural networks are highly over-parameterized. So there's little to prevent them to practically memorize your training data. So we have seen in the Pokemon examples that in some architectures you have way more network parameters than you have images. Right? So we have to make sure that the network doesn't go this fast to that regime. So I'll be still using some examples from regular machine learning to understand a bit how overfitting occurs and how we can solve this with regularization. So I'll just use a simple example with a polynomial fitting. So we have these these points generated from this curve with some random noise, and we want to find function the parameters of a polynomial that would fit this function, right? So what we'll be doing here, we'll be playing with the degree of the polynomial, meaning that we'll add up in complexity. So here for a polynomial of degree 1, we can see that we have a straight line. So it does as best as it can, but it cannot be expressive enough because it doesn't have much capacity. And now we have a polynomial of degree 2, so we can see that we have this curvy shape already, and this allows a better fitting of the curve that generated. polynomial of degree 4. Well, sorry, I think there was a mistake. So 3, now 4. So we can see as we increase the capacity of the model, the easier is it to fit this training data, right? So you practically memorize it. So this neural networks, in particular deep neural networks, are very prone to have this type of overfitting of just memorizing the training data. So and we'll just to plot it exactly what has happened, so we can see that our sweet spot should be somewhere at degree 4. So we have here the degree of the polynomial with respect to the error, in red the test, and in green the train. So we can see that after degree 5, there's a divergence between the test loss and the test error and the train error. So it's clear here we are entering the overfitting regime, and well, the sweet spot will be somewhere here at 3 and 4 degree. So well, regularization in deep learning. Well, if we take the sorry, there was a typo here, so I'm speaking here of the capacity. So although it's quite difficult to define precisely, it's quite clear in practice how to increase or decrease the capacity given a class of models. So for example, if we are speaking of polynomials, it's changing the degree. If it's a neural network, the capacity consists in changing the number of layers in a neural network, or the width, or changing actually even the number of training iterations. Or another way of controlling the capacity is with regularization terms. So we will be speaking now about how to control this into regularization terms, because they are a tool that can be used also in the polynomial case, but also in the neural network case. They're a generic tool for regularization, for allowing for avoiding overfitting and enable the network to generalize better. So to give you a definition of regularization, well, I think the easiest one is the one provided by Ben Recht, that calls the regularizes anything that hurts the training process. So practically in deep neural networks, since they have this speed of going towards the minimum and to find the solution from the samples that we get quickly, because it has this huge space of hyperparameters. What we want to do in regularization is practically to prevent it from going this fast there. So with regularization, we actually try to hurt the training process. So we can see that the most simple example of regularization is this one. So we take our loss as before, which is the reconstruction loss, or mean squared error loss, where we want to reconstruct the solution to make it as close as possible with the ground truth. So what we change here, we add just this term, rho with the sum of the square of the weights. Right? So, well, the question is, what will happen now? So we know that we want to minimize the loss. So this loss will be going towards 0. We know that we want to minimize this, so this should also go to 0. So we can group. So this means that also the impact on the loss will be that these values will also go to 0. And that's what we try here to regularization. With regularization, is not to leave much room to move for our weights. We'll be practically constraining them to have a certain range of values. So we call this L2 regularization, or also we call it, well, in Bayesian literature, is also called the Gaussian prior on the weights, because in the end, they will eventually follow a Gaussian distribution centered around 0. So let's see the impact of regularization on a function. So we have the same problem as before. We show it here. Well, it's an example from François Fleuret. He shows it for several initializations. Were several data points from this curve. It shows how is the final solution when we have a polynomial of degree 9. So it was the messy one, and a big regularization. So rho here is 1, but this 10, sorry. So then we go to 1. So we have a regularization term of 1. we can see that we have a lot more room in a lot more diversity in the solutions. Practically, we give more liberty in the space of the weight, so we have a bigger diversity of solutions. And as we start decreasing the regularization, we can see that there's a lot of more wiggling happening in terms of the solution. So again, these curves start to go towards memorizing the data points, right? So as I loosen the regularization, we can see that it starts to go overfitting again. The one when I go there's no regularization, practically there's it's nothing to be useful here. So you can see that each time when we run our algorithm, we actually have a different solution. So this is quite annoying. And we that's why we actually need a regularization, and it can happen with neural networks quite common. It's quite a common problem. So we can see here the same curve that but now based on the regularization value. So when we have practically almost no regularization, the train loss is 0, while the test error goes sky high. So the sweet point should be somewhere here. So we actually, that's why I was mentioning L2 regularization, because it's quite common in deep learning. You can find it in all optimizers. So, but the common name in deep learning is weight decay. So you will always see that you have well, whether it's SGD or Adam or other variant of Adam or other optimizer, you can see that you always have this parameter weight decay that allows you to include to add L2 regularization in your optimizer. Okay, so far we have explored some generic regularization methods, L2 in particular. In the following, we will actually discover some strategies for regularization that are specific to deep learning, and that have different ways of acting. So they're not just impacting the loss; they are actually introduced as layers, or they in the architecture they give they impact optimization in a similar way with a regularization, but have a different shape. And I'll see you in the next module for discovering them. See you later. Bye bye.